All right, here's just a quick video to kind of summarize some of the stuff that we've been doing in 1.2.4. This is actually kind of a 2-day lesson for us, so it'll be broken down into some of the items where we talk about these review words and factors, factor pairs, and properties of numbers. And then when I transition to prime factors and factorization in this video, that's kind of really our part 2, and that's really the video the support that we'll have. I believe that'll be starting early next week is when we'll first do that. So it's a very quick review for 124. Make sure that you're kind of writing in your notebook kind of a heading, right? And in this case, this one is really, I think you could just label it the products, factors, and factor pairs. Okay, and that'll be that focus for today, and you could just put today's date on there when you're writing in your notebook. Good spot for things to be kind of written down and for you to reference back to. So even numbers all end in 0, 2, 4, 6, 8. And then if they end in 0, 2, 4, 6, or 8, then other numbers that are good then would be 10, 12, 14, 16, right? 18. And that goes on and on and on forever. Okay, it's not ending. And then odd numbers are, well, all the other numbers. They end in 1, 3, 5, 7, 9. If they end in 1, 3, 5, 7, 9, then of course 11, 13, 15, 17. And again, those go on forever, right? To 19, 21, 23. All right. So prime and composite, again, numbers that we've talked about before. So quick check on revision on that. Prime numbers are numbers that are always 1 times, I'll just refer to it as itself, right? 1 times itself are the only numbers that will multiply into something. So something like 3, because the only numbers that multiply into 3 would be 1 and 3, right? 19 is 1 and 19. Where something like 18 is 1 and 18, but it also has 2 and 9. Also has 3 and 6 too. So that's why it makes it composite. It's composed, the word compose is in composite, of multiple things to make that number. Okay. Another prime number would be 23, 31. Those would be other choices. Other composite numbers would be numbers like 21, because of 3 times 7 makes that composite. 25, because 5 times 5. 15 would work, right? So there is an infinite number of primes, and I'm just going to put dots on there indicating that there's all of them. And we didn't even write all of them in here, right? 17, 5, 7, 11, all of those are still in there too. And composite also go on forever. Okay, so that was that super quick review, but I think it's really important to understand these items before we get into the other part where we talk about these products, factors, and factor pairs. Okay, so in class we kind of played a little bit of a game with factor. Oh, I'm drawing a blank on the game, but you didn't score as many points, and you could give your opponent more points if you chose numbers that were more composite type numbers. You would help your cause, you would help your chances of winning if you could use prime numbers. So it encouraged you to use prime numbers in order to do this. So let's talk a little bit about these when we talk about factors and factor pairs. So if you saw the 1.2.3 stuff within Canvas, we talked about different arrays. So if I have the number 17, you can make an array, right? An array for that. And that array is going to be 17 dots. Now, a quicker way for mathematicians to do this is not to draw these individual dots, but instead to just basically make a rectangle that represents that. That's an array, 1 by 17 pennies. They're all lined up. Well, we also can refer to this as 1 and 17 as factors of 17, right? So here's a definition, and I did Highlight that a little bit in one of the videos, factors. It's an important word for us to know, right? And then what happens is we can take these factors and we can have the product of them. That means multiplication, product. Whoops. Not a very good O, or T for that matter, huh? Let's fix that. Product is multiplication. Multiplication. And when we take those two factors, like this case, 1, and we take the product of that with those factors, we have what's called a factor pair. Right? Pair means two. A pair of shoes, right? A pair of socks, those come in twos. Quite honestly, I don't know why they would say pair of underwear, but that doesn't matter. Anyway, so we have factors and we have factor pairs, okay? So 17 has two factors, but they have one factor pair, all right? Now remember, 17 is prime, right? Prime. So we only had one array that we could create with that. Let's choose a little bit more difficult problem, one that has a little bit more action in it here, okay? Let's choose something like 24. Whoops. Something like 24. Okay. Well, if I'm going to list all of the factors, I actually like to list the factors kind of in pairs right away. Maybe not as a product, but still. And this is how I like to do it. I like to start with the smallest number, 1, and I say what number multiplies with 1 to get to 24. There we go, 124. Then I choose the next number, 2. Notice I'm going up in order, 2. Does 2 go into 24? Yes, it does, 12. Does 3 go into 24? 3 and, yep, 8. How about 4? Does that work? 4 and 6. Then I would choose the next number. How about 5? 5 and, that's not going to work, is it? So we don't use 5. And then I notice that if I were to do 6 here, I'm already starting with these numbers, right? So if you look at it, by choosing to go up, going 1, 2, 3, 4, 1, 2, 3, 4 here, what I've done is I've already started to work the other side, the other numbers that I would possibly need right there. Okay? So what are these? These are all of our factors, right? These are the factors of 24. Now I kind of put them in pairs, and you could call them a factor pair, I guess. I don't know if they have to have a product in there to be necessarily considered a factor pair. But if we wanted to do factor pairs, right, pairs are in 2, we could just simply say 1 times 24, right? 2 times 12, 3 times 8, 4 times 6. Those are our factor pairs. Now, let's take a second, step back. What type of number is 24? It's composite, right? So if it's a composite number, it's going to have composite will have more than 2 factors. Okay, we bounce back up here. How many factors were there for a prime number of 17? Just 2, right? So composite has more than 2 factors, but it also has what? It also has more than 1. Whoops. Got to finish the word then. Than 1 factor pair. Every number will have the factor pair of 1 in itself. It's these that make it composite. Okay? All right, so now to try to keep the things moving, we're going to move to kind of the part 2 thing. So this will make this video a little bit longer here because of that. And what we're going to do is we call this prime factorization. Okay, prime factorization. So what we'll do is let's start with that number 24. Okay, now this is going to look different than what we saw up here, okay? Prime factorization, we'll start with our number 24. I like to use it kind of like more like a tree, and I'll show you what I mean. So what are we going to do? We're looking for a factor pair of 24. Okay, let's look for a factor pair of 24. All right, so that factor pair could be 4 times 6, right? That's a factor pair of 24. We found the two numbers that multiply to 24. Now what I'm doing is I'm going to continue to break down these numbers until I only have prime numbers left, okay? So I look at the 4, and what do I notice? Well, 4 is not prime, so I'm going to break it down until I get to primes. 2 times 2 are factors of 4. Now keep in mind, I'm really taking 2 times 2 as another way of writing 4. I still need to multiply it by 6. And what I'm doing is I'm looking for the prime numbers of 6. The prime numbers of 6 are 2 and 3. All right, so now I take a look and I say, is that prime? All those numbers are prime. So I'm done. 2 times 2 times 2 times 3. Okay, so now let's try a different factor pair for 24. So another factor pair of 24 that you might have been thinking instead of 4 and 6 was maybe 3 and 8, right? So I look at it and I say, is 3 prime and is 8 prime? And the answer to that is no, 3 is prime. So I'm just going to kind of put it down here. And then I'm going to find the factors of 8 because 8 is not prime. So I could put it down and I have 2 times 4, right? I take a look. Prime, that's good, but 4 needs some work. Okay, so 3 times 2 times 2 times 2. Okay, well, looks like I have just primes there. Well, let's take a look at something. Take a look at this prime factorization and compare it to this prime factorization. The question is it the same? The answer to that is yes. Yes, it is. And the reason we know that it is the same, even though they're not in the same order, goes back to the commutative property that we probably had, I think that you had seen in elementary school. The commutative property says, for multiplication, says this: 2 times 3 is the same as 3 times 2. 2 times 3 is 6, but 3 times 2 is 6. So we can switch those two numbers and it's the same. So when I look at this first one, the 3 is at the end. When I look at this one, the 3 was first. Guess what? It doesn't matter the order of it. Those are the exact same. Okay? Now we can do this for any number that we want to. Something like, very quickly, I could do 21. 21, I would break that down to 3 and 7. That's the prime factorization of 21. Now, what's very cool, factorization, I think I spelled that right, hopefully. Looks a little off, but the cool part is this prime factorization, 3 times 7, is only for 21. It never works for anything else, okay? All right, so one last component to put this together. We're mathematicians, right? We want to write this a little quicker. So many years ago, I'm going to take this and I'm going to move this down here, okay? I'll actually do the first one. 2 times 2 times 2 times 3. So many years ago, mathematicians, many years ago, they only had addition, right? They do 2 plus 3 plus 4 or whatever, right? Well, then eventually they started doing 2 plus 2 plus 2, and they said, hey, we got to do a quicker way of putting this together. So they came up with multiplication. Instead of 2 plus 2 plus 2, they would write 2 times 3. So that was so much easier for them to instead write a bunch of repeated additions to make no multiplication. Well, guess what? We as mathematicians have a quicker way of writing what we call repeated multiplication. When we have 2 times 2 times 2, instead of writing it as 2 times 2 times 2, we have a different way of doing it, and we call it as an exponent. So 2 times 2 times 2 is 2 to the third power. Okay, what does that mean? That means that it is 2 times 2 times 2 3 times. Okay, and then we have to still bring down our 3. So that's 2 to the third power times 3. Okay, I'll make one up here. Let's go 2 times 2 times 2 times 3 times 5 times 5. Not even sure what number that makes right now. 100, 600, I think. Okay, so 2 times 2 times 2, what does that become? Well, just up above, we wrote that as 2 to the third power, because it's 2 times 2 times 2. 3 is already by itself, so we're just going to drop that 3 down. There's no repeated multiplication. And I look and there's repeated multiplication for 5. So I drop that down and I make that 5 to the second power. Why? Because that's 5 times 5, okay? So this is a different way of writing it, and we're going to start using a lot more exponents. Okay, hopefully that helps. If you have any other questions, let me know. Again, this is 1.2.4 Part 1 and 1.2.4 Part 2.